Hello everyone, welcome to 2021 Esri Developer Summit. My name is Zikang. Today, my colleague Wenxue and I will be present ArcGIS Online Imagery and how to work with hosted ArcGIS Online imagery layers using the ArcGIS API for JavaScript. ArcGIS Online Hosted Imagery is a new product we're trying to offer. Here's an overview of it. It is a complete imagery solution, web imagery solution, which including the hosting imagery, we serve the imagery, and we offer a lot of out-of-box imagery analysis tools for you to use them and generate new hosted layers and stored on ArcGIS Online. Let's talk about the image storage part. Users can upload the imagery files, then ArcGIS Online will process it and securely stores them in the cloud. Once the data is put into the cloud, the ArcGIS image server at the backend of ArcGIS Online will serve the hosted image files as hosted image services, and eventually each of them will be exposed as hosted imagery layers. There are two types of hosted imagery layers. The first one is dynamic imagery layer. It offers the capability to access the imagery dynamically with the server-side processing and rendering. So all the process will happen on the server side, and server returns you the processed images, and you will be able to view the processed images out of box at client side. Another layer types we are offering is tiled imagery layers. As the name goes, it's trying to access the static image tiles of the tiled image service if it has. We will offer the client-side processing and rendering, all stuff like that, but everything stays at the client side. Server only provides basic image metadata and all the tile caches. It is a client trying to draw the tiles and do all the processing work. And the last one is imagery analysis. Imagery analysis are essentially the geoprocessing service at the backend. It will take the hosted imagery layers as input and start running those geoprocessing services. And as a result, new ArcGIS Online hosted imagery layers and other feature layers in some tools will be generated and ready to use. As you can see, it is a circle. We start from the uploaded image files all the way to expose them, share them, and doing extra analysis on top of that to generate new type of layers. So this is a whole web GIS imagery solution. We are doing host, we are serve the imagery. We offer your tools to analyze these imageries. As ArcGIS Online hosted imagery is a new product, I'm going to talk about how we can create a hosted imagery with the image files we have, and eventually how the layers will look like. We have a guided wizard to help you upload images and configure the hosted imagery layers and all properties associated with those layers. First, we will ask you to choose layer type, whether you want a tiled imagery layer or a dynamic imagery layer. The next step will ask you to select how the uploaded image files will be organized and managed, such as, for instance, I have a collection of images, and I want to use the traditional mosaic dataset technology to organize everything, and I want to access each of the rasters as a collection. Then probably I need to go with the image collection option. Or as an alternative, I just want to mosaic all the images are uploaded together and generate a single raster file, and I'm okay to just play with that. In this case, you need to select the one image mosaic option. And in some cases, I just want to publish each of the images I uploaded as a single hosted image layer. And we have option for that as well. The next step is define imagery. Here, we offer you more fine-grained control on the layer configuration. You can define a raster type for the hosted image layer you are trying to create, and you can define a template associated with that as well. And we offer you a UI to help you upload the image files. You can drag drop a folder to upload, and you can also select each of the image files you want to put in the upload drop box. And at the end, you can set the item details for each of the hosted image layer items you are trying to create. For instance, the tags, the descriptions, and the name for each of the items. I'm going to give you a demo on how we can use ArcGIS Online create image layers wizard to create hosted image layers from image files at hand. I logged into my ArcGIS Online account. Under the Content tab, there's a Create button, in which we have an option to create image layer. It's still in beta, and only EAP user can access this feature. Once I click that button, it brings me to a full page of Create Image Layers user experience. At the first step, I can select which subtype I want to create as a hosted image layer. By default, tiled image layer is checked. It will provide you the image access as static tiles, and we support client-side processing and rendering. So the client-side access and fetch the static tiles from the server, and all the processing happens at the client-side. As a comparison, a dynamic image layer. This is a traditional option. If you are very familiar with ArcGIS Online image layer, it will connect you to the dynamic image server and use the image server's operation to do the task. It supports server-side processing and dynamic mosaicing if source is a mosaic dataset. It can help you manage a collection of images. So the main difference is tile image layer is to help you get the tiles, and the processing is at the client side. But for the dynamic image layer, the processing is at the server side, and you only get the processed result from the server and directly use them for display. More so importantly, both of the layers are available to be used as input for raster analysis tools. For this time, I'll select Dynamic Imagery layer for this demo. In the next step, I'm offered 4 layer configuration types based on my selection. I can upload one image and publish it as one dynamic image layer. And I can upload multiple images and the ArcGIS Online will try to mosaic them all together and generate one output image files. And eventually publish that one file as a hosted image layer. Alternatively, all the uploaded images can be managed under an image collection. This is very similar with our mosaic dataset, in which you will have a footprint table, manage all the images using a single hosted image layers. With this layer, you can dynamically mosaic the images and access each of the images independently. And the very last option is the multiple image layers option. It's a batch mode of the one image layer. It will create multiple image layers for all of the uploaded images you will upload in the next step. At this time for the demo, I will choose Image Collection. At the next step, I can define the imagery. At first, I can choose the raster type of the images I'm going to upload. I'm going to upload the Landsat data, so I'll choose Landsat 7 ETM+. Inside the configure properties, you will be offered a lot of fine-grained control to adjust, such as what's the resampling type you want to apply on the layer, and what's the processing templates you want to apply to the images when creating such image collection. There are lots of things there for you to navigate and play with. For this time, I'll just keep everything as default. And I can browse to the folder that has my data. I can drag and drop the Landsat data, and it will automatically crawling all the files inside the folder. You don't need to wait until all the files is uploaded. You can go to the next step to set some details, titles, names, tags for the layers. For this time, I'll just say Landsat 7 Dynamic Imagery Layer. T. Tags Landsat. Tags DIL for dynamic imagery. And I can click create button to let you run through. It will take a couple of minutes to upload the images and eventually create such image layer for you. It's all depending on your network speed and how big your data is. I'm going to save us some time, and I'll bring back to the page after we have the image layers created. Okay, Here's the item we just created. You will see the type is imagery layer, which we already have before. But now we have a bracket having hosted. So it's hosted by ArcGIS Online. The data, the service, everything is managed by ArcGIS Online. So it's a little bit different when you're comparing with traditionally you try to add an atom from a third-party URL, image server URL, and that atom just a very small thing in your ArcGIS Online. It holds a reference to the real image service. This is different. Everything is managed by ArcGIS Online. And if you choose to create a tiled imagery layer, you will have a item like this. Okay, let's get back to our PowerPoint. As I said, dynamic imagery layer type is really the old traditional imagery layer if you are familiar with ArcGIS Online. And the tiled imagery layer is a new offering we have. So the question is like this. Why do we have this? What's special about the tiled imagery layer? Here's the thing. So for tiled imagery layer, the backend of it is a tiled imagery service. The layer will interact with the tile part of the image service. But the tile is really the magic here. We can enhance the tile cache capability. We invented a new file format, CRF, for this workflow. So for instance, at the create image layer step, you are trying to upload a bunch of TIFF files and trying to do an image mosaic for all these TIFFs. Eventually, they will be converted into a CRF raster after we mosaic them together. For the CRF format, what's special about it? So it's one of the trending image formats at ArcGIS. It has all the image metadata and key properties. So it's like traditional TIFF raster format, but it is also a tiled image format. If you view the structure of the CRF, it's essentially a set of tile cache. For the tile cache, it is actually encoded with LERC by default, and we also support JPEG+. So comparing this encoded format LERC with traditional like JPEG or PNG or some other formats, the real advantage is the LERC we support rasters with flexible pixel bit depths. It supports 8-bit, 16-bit, 32-bit, signed and signed integer, and 32-bit floating point, things like that. But for JPEG PNG, it's only like 8-bit. You can only represent 0 to 255 on each of the RGB channels. That's it. That's a pure picture, RGB pictures. But for this tile cache, it's really the rasters. We support multi-band as well. And where it is multi-dimensional, we will support multi-dimensional in this set of tile cache. So if you view this CRF format as a whole, you will realize it's a combination of traditional raster format and tile cache. And because of this combination, it is optimized for reading and writing in a distributed processing and storage environment. So even though we call it tiled imagery layer, you feel it's like just pictures for viewing, but essentially it is not. It's the cache itself is the new cache, the CRF cache. It has all the traditional raster features, and also it's exposing as a set of tile cache. We just reviewed the whole workflow of creating and using a ArcGIS Online hosted imagery. And let's take a look at how JavaScript API can interact with the layers. There are two APIs involved. The one is for imagery layer class. Another one is imagery tile layer class. These APIs are designed for interacting with the backend image services of the hosted imagery layers. For dynamic imagery layers, you will need to use the imagery layer class. It will act as an agent to dynamically interact with the backend service, and server will handle the processing work for the data. And at the client side, you just take the pictures and get information from server, just use it. On the other hand, for tiled image services, which is used by tiled imagery layers, you will need to use imagery tile layer. As I said, this is a new API, and it represents raster tiles from a tiled image service. So once you get all the tiles, all the processing work will be handled at the client side. Here are two references you can use to work with these two layer types. If you use the imagery layer class to construct a layer, you can interact with a dynamic imagery layer. And you can set the rendering rule or renderer property for the layer to set up for server-side pixel processing and rendering. On the other hand, you can use pixel filter property to try to get the pixel blocks of the dynamic image service. And with the pixel blocks you have, you can do extra customized processing at the client side. If the source is an image collection or a mosaic dataset, dynamic imagery layer will have the footprints for each of the rasters inside the image collection, and the imagery layer will be able to help you view and query the attributes of them. Also, you can identify pixel values and other raster attributes and bring them to the pop-up window of the imagery layer. All the operations are being sent to the server. Server processes your request and send back the response to you, and you just bring out the information to the pop-up window. Server side also has static legend information. With imagery layer, you can access the legend picture and bring it to your web application. It also offers you the capability to compute the statistics and histograms of the imagery layer with the geometry you send it to the layer. If the source is a multidimensional or a mosaic dataset, we offer the full support through imagery layer as well. And if the default projection of the imagery layer is different with base map, And this layer will help you to get reprojected to have it align with the base map you have. An export image request will be sent to the server. Server will process that request and get back the image you want. We have a lot of other capabilities as well. You can view it inside the API reference I sent you in the last slide. Another related JavaScript API class is Imagery Tile Layer class. It represents the raster tiles from a tiled image service, which a tiled image layer will be using. It will try to fetch the tiles from the service and all the other associated properties, such as legend, statistics, and histograms, the multidimensional info if it has, and raster attribute table, things like that. But all the processing and rendering work for the tiles are happening at the client side. We spend a lot of times in JavaScript AI to make it working perfectly. We can have the equivalent support for pop-up as with the traditional imagery layer JavaScript API class when you work with dynamic imagery layer. We can fetch the pixel values from the tile cache and display all the raster attributes of it and bring all the information to the pop-up window. We can also do reprojection. We can reproject the tile cache to whatever the base map use to make it look well. We also support multidimensional filtering by using multidimensional definition, in which you can specify what variables and dimensions you want to see, and we will bring it to your layer and have that displayed in your web map application. We have a lot of others to offer as well. Please check our API reference, and my colleague Wenxue will talk about some demos and really dive into the code snippet of these two imagery layers, and hopefully you will like those as well. The first demo is about dynamic imagery layer. We're going to use imagery layer to access it and send some server-side raster functions and have the server process it and return back the images to us.
Dynamic image service offers on-demand server-side mosaicking, processing, and rendering capabilities, in addition to a catalog that you can search and query imagery metadata. In JavaScript API, the imagery layer class has a mosaic rule property that you can use it to define how you want to mosaic the images together. In this demo, I want to show a single landside scene in the image service through the lock_raster method. I specify the lock_raster method and provide the raster ID. Image layer also has a rendering rule property through which you can define additional processing. There are more than 100 system raster functions you can use. In this case, I'm going to show you a simple case of chaining two raster functions together. First, I define an NDVI raster function, which takes the infrared band ID and the red band ID. You can query the key properties for the band information, which is available on layer.service raster info. Let's look at the key properties. Among key properties bag, you can find band properties. It lists the names of each band, corresponding wavelength, etc. With this, you know the band ID of the near-infrared band and the red band, which you can specify in the NDVI Raster function. The output of the NDVI function is the input of color map function, which you use a color map to visualize the result. You can either specify an array of value to color lookup mappings or use the built-in color ramps. In this case, I'm using an existing color ramp name. This processing definition is sent to image server, processed on server, then rendered on server, and returned back to the client. We can take a look. What's being sent to the server is it converts this Raster function definition to the JSON format, which has the NDVI and the color map that you specified. In addition to server-side rendering that returns a ready-to-use JPEG PNG format, you can also ask raw data from the image server by specifying the look format on the image layer. Let's take a look at this SDK example, which provides additional pixel processing after it retrieves the raw pixel data from the server. It defines a colorize function, which uses a special colorization method to visualize the image, set the pixel filter on the layer. So pixel filter is a way to perform additional processing and do customized rendering.
The second demo is about dynamic imagery layer as well. We will bring in a vector field data to display the magnitude and direction of the wind.
The imagery layer class in ArcGIS API also supports vector field render that you can use to visualize vector field data. This type of data typically represent ocean current or wind speed. Previously, in 3x API, we had to use a different type of layer called ArcGIS Image Service Vector Layer to perform visualization on this type of data. This is no longer needed in 4x. The advantage is you have the ability to use a different render, such as stretch, on this type of data. To use this render, when you create the image layer, you can specify the corresponding visualization style, such as Beaufort wind, ocean current, or wind barbs. You get to specify the flow representation, the symbol tile size, and some visualization variables. This type of data is typically multidimensional. You can choose to display the image service at a different time. What's happening behind the scene is image server will convert this configuration into an export image request to request data at a particular time, and in addition, ask the server to perform vector field resampling. What's returned from server is raw binary data compressed in look format. It's highly compressed. You can see the size here. It's only a few kilobytes. The response is decoded in JS API, and for each pixel, it attaches the magnitude and direction information from the two raster bands, then convert it into vector symbols to display.
The third demo is about tiled imagery layer. We're going to use imagery tile layer to access it, the semantic data. We're going to show you examples how to access the legend, pop-up, interpolation, and reprojection for this layer.
In this demo, we'll go through the basics of imagery tile layer. I have a hosted tiled image service that shows national land cover data. It covers the lower 48 states using Albers equal area projection. To work with this image service, we use the imagery tile layer class in JS API pass down the URL of the tiled image service. When we create a map, we specify the layer as the operational layer. With just a couple lines code, we can now display the image service on a map. It's as simple as that. If you want a little bit extra, you can configure a pop-up template. In this case, I want to use the layer's default template. So when you identify a point on the screen, the layer will return you a pop-up with a pixel value at the current location and the corresponding land cover class name, along with other information. You can also create a legend widget and add it to the map. Furthermore, the layer has a built-in mechanism to figure out what's the best default interpolation it can use for the specific data. In this case, it's categorical data, so the layer actually uses nearest neighbor resampling so that it doesn't really create pixel values that doesn't exist. So you can actually specify different interpolation, such as majority, if you want to see the overall trend, overall distribution of land cover. Now let's take a look how it works behind the scene by inspecting the network traffic. So when this layer is added to the map, it goes through layer initialization. So in this phase, it fetches the service info from image server endpoint and get the basic information of the raster, such as band count, extent, spatial reference, pixel type, tile information, etc. Then it fetches additional metadata the image service may have, as indicated by the flags on service info, such as raster attribute table, histograms, key properties, etc. So when all the information are returned from Imagery tile server, the layer will be able to establish a complete raster information model. It's important to note that tile imagery is not basemap. It's a full-blown remote raster dataset. That's the fundamental difference between a tiled imagery and the traditional cached image services. The layer not only uses the raster information to locate and decode raster tiles, but more importantly, it leverages all the metadata to create a smart default renderer, get a default band combination for multispectral dataset, and configure a default interpolation based on the data type. You may notice in the code that I don't have a renderer specified. I'm actually leveraging the default renderer. Now let's take a look. This layer represents categorical data. You can see the layer is smart enough to figure out that part and use the information from the raster attribute table to construct a unique value renderer for me. The default renderer is typically good enough for most use cases. If you have a different visualization requirement, you can always create a renderer and set it on the layer. When map navigation, such as zooming and panning, happens, it triggers tile fetch. You can see what's returned from Imagery tile server is raw binary data compressed using log compression. The layer fetches raster tiles in the current view extent, fetch them in parallel and decode them in parallel using multiple CPU workers. It extracts raster bands if necessary, such as multispectral data case. Then it performs projection, resampling, and rendering in GPU. Now let's take a look how projection works. In this case, when I create the map, I specified a base map. Actually, that's the only thing I did to use projection. The layer does all the work to make the process automatic and transparent. As an app developer, there's nothing else need to be done besides providing a base map. To summarize, Imagery Tile Layer is a fat client. It works just like ArcGIS Pro. It establishes a complete raster information model, handles imagery decompression, tile mosaicking and clipping, projection, band extraction, resampling, and rendering on the client side. This rich set of functionality is now available at your fingertips.
In next demo, we're going to show you how the tile imagery layer works and how we use the Imagery Tile Layer API to fetch the tile caches, but really it's real rasters. How we fetch the pixel blocks and process them and generated a pie chart out of it to reflect the land cover type category in a small circle.
Imagery Tile Layer always need to fetch and work with raw pixel data along with raster metadata information to display tiled image service on a map. The layer has a raster info property that lets you access all the raster metadata, such as key properties, histograms, raster attribute table, etc. It also has a fetch pixels method that you can use to get the pixel block within a given extent and resolution. When the layer view finishes drawing update, you can invoke this fetch pixels method, passing the view's extent, width, and height. What the layer is going to do is to simply assemble all the tiles from its raw pixel block cache, mosaic them, project them, and clip them to the extent boundary. Let's take a look at the final result here. It has the extent that you specified and the corresponding pixel block. The pixel block contains pixels that represent all raster bands. Each raster band has a certain number of rows and columns as identified by height and width property. The pixels in a raster band is arranged in a row major order. It writes all the pixels in the first row, then move on to the second row, then the third row, and so on. Now, let's pick a point on the screen and see what happens after that. The screen that you identified has a row and column offset. That's basically the row and column offset on the pixel matrix in the pixel block. Since you know the map view's resolution, you know how many pixels are covered by the 1 mile radius buffer. With a little bit of math, you can filter them and accumulate all the pixels in this search radius, then send them to a chart. Voila! Now you have the land cover type distribution within 1 mile search radius of the screen point that you identified. It's worth noting that this application was ported from an existing SDK example that uses dynamic imagery layer. Basically, you have the same ability to access raw pixel blocks and do similar apps using Imagery Tile Layer.
We also have an elevation tiled imagery layer, in which each of the pixels inside the tile cache is a real elevation value. We're going to apply a client-side shaded relief renderer to adjust the appearance of this layer.
To better support elevation data visualization, we introduced shaded relief renderer in JS API. It's supported by both dynamic imagery layer and imagery tile layer. For dynamic imagery layer, we support the rendering on server side, but for imagery tile layer, it's only supported on the client side, simply because Imagery Tile Server does not provide any rendering capability. The client-side implementation is done entirely on GPU, so it's really fast. You can change the shaded relief parameters interactively, such as hair shade type, light source position, exaggeration factor, color ramp or without color ramp, etc. To use this render in the code, you simply construct a raster shaded relief render and provide all the properties that you need to use. Then set that on the layer. So raster shaded relief render, just like all the other renders, we support auto casting. One important feature of client-side rendering is, since it is implemented on GPU, we support alpha transparency as long as the render supports color input, such as single band stretch, shaded relief render, unique value render, class breaks render, or color map render. In this case, I specify the first part of the color ramp to be transparent. Now let's take a look at how shaded relief render works. But first, you need to stretch the elevation, then colorize the elevation using the color ramp provided. Then convert the colorized result to HSV space and fuse with the hair shade in HSV space, then convert back to RGB before displaying it. And since I specified the first part of the color ramp to be transparent, the transparency is carried over throughout the process. As a result, area that has low elevation will be displayed transparently, so you can see through the elevation service layer and get the base map displayed. As a result, we are now displaying shaded relief, but only in the mountain areas. It's worth noting that this render is also supported by 3D scene view.
In the last demo, we are going to show a tiled imagery layer example as well, but this time we have a multi-dimensional tile cache. We are going to show you how to filter and displace each of the slices inside a multi-dimensional tiled imagery layer by filtering through the variables and dimensions it has.
Imagery tile layer supports multi-dimensional data. When you publish an netcdf to ArcGIS Online, it creates a hosted tiled image service that has multi-dimensional info. It serves tiles for different variables with different sets of dimensions. Let's take a look at the image service endpoint to check out the multi-dimensional info. This service has 5 different variables. Each variable has its own set of dimensions. For example, the water temperature variable has 2 dimensions, standard time and standard z. Each variable may also contain information for its own statistics and histograms that you can use it to visualize the variable better. The image service also has a slices resource which provides mapping from a multi-dimensional definition to a corresponding slice ID. The imagery tile layer will use this internally. When you specify a particular slice through dimensional definition, it converts it to slice ID, then asks the imagery tile server to deliver the corresponding data. So when I change this slider value to use a different depth for the salinity variable, what happens is in the code, I update the multi-dimensional definition property to specify the corresponding dimension values, then set it on the layer. When I choose to use a different variable, I update the corresponding variable name in the dimensional definition. And at the same time, I want to update the render to use the statistics for the chosen water temperature variable. Basically, Imagery tile layer has multidimensional data support just like dynamic image layer and follows the same multidimensional information model and use similar programming patterns.
Thanks for joining us today. Please provide your feedback for this session by clicking on the session survey link directly below the video. Thank you. Have a nice day.